Okay, hello everyone and welcome to this next lecture on Python Power Electronics. And this time I'm going to start this lecture with the basic Google page. I'm going to take you to the website and I'm going to go through the animation corresponding to the tutorial. So to begin with the website, I would just Google Python Power Electronics and the first link is my website. And on arriving at the website, all you have to do is go to tutorials, because this is a tutorial that I'm going to conduct. And there are a lot of tutorials which you can always go through. The previous tutorial, the video lecture, was based on this tutorial, that is the simulation model of a photovoltaic panel. Here I described how you can simulate a photovoltaic panel. In this tutorial, I will take on the next topic, and that is how do we control the DC to DC converter for extracting power from a PV panel. So let's click on this link and this takes you to the report which is based on this. So there are lots of links here, you can just go through them. It has a report. I'll click on this, and this report is basically a PDF file which is more or less an instruction manual on how to use the simulation files corresponding to this tutorial. Okay, more on this later. The most important fact is the slideshow or the animation, which is what I'm going to use as a visual for this video lecture. So I'm going to open this in a new tab, and this is it. So this tutorial or this animation or slideshow is made on JavaScript, so it can be run on your web browser. So for that reason, I'll be using my web browser. In this case, I'm using Google Chrome, and I would recommend that you use Google Chrome or Mozilla Firefox, as the JavaScript which is used in this may not render very well in the older web browsers. Like, it may not run very well in an old version of Internet Explorer. So my recommendation is Google Chrome. Now in this tutorial, there are several links here which I will take you to later, but most important for this tutorial, you need to use these three buttons. Now the first button on the left, the first button on the right rather, is the button to go forward. So if I click on this, I just go forward between slides. The button on the left is the reverse button, so it is to go backwards, and this way I reach the front page. Now I'll be using this one. This is just basically, all it does is it provides this little bit of a visual fading in and fading out. For example, as I click on this, you'll see this slide fades out and the next slide fades in. It's just an effect, we don't have to use it, but I'll use it in this case. So to start off with, this tutorial is going to talk about how to switch a DC to DC converter that interfaces the PV panel so as to extract power from the PV panel. So as you can see, this basic slide just tells you how to use this. It tells you to use the play buttons to go forward and backward, and that's what I will do. So let's start off with this tutorial. Okay, to start off with this, the figure here shows how a PV panel is integrated to the grid. Now, just to describe this PV panel, as I said before, a lot of manufacturers produce PV panels of different specifications. Now you need to look at it. In general, when a PV panel is intended to be connected to the grid, the voltage of the PV panel is usually between 20 volts and 40 volts. Usually. There are higher voltage PV panels, there are lower voltage PV panels. But I'm going to consider the PV panel voltage in this to be around 30 volts. Now, the grid here can be very, very different. For example, this grid could be a single phase grid, it could be a split phase grid, or it could be a three phase grid. Also depends upon the region or the country. In North America, a single phase grid would be 110 volts or 120 volts, whereas in Europe, a split single phase system could be 240 volts. Also in North America, the frequency of the grid is around 50 Hertz, whereas in the rest of the world it's the other way around. In North America, the frequency of the grid is usually around 60 Hertz, whereas in the rest of the world, in Europe, Asia, it is usually 50 Hertz. So therefore, this converter is extremely important. We need to convert DC to AC, number one. Number two, we need to step up this 30 volts to a voltage that could be anywhere between 110 to 240 volts. Let's take this to be around 200 volts. So let's go to the next slide. So in this next slide, I am showing you one sample conversion process. There are lots of them, but I'm just showing you one. There is also a possibility that you can do this conversion in one step. There is a possibility, but I'm going to talk about the most popular way, and that is the two-step conversion. That is, there is a DC to DC converter that interfaces the PV panel to an intermediate DC bus, that is a DC capacitor. And there is a DC to AC converter which now converts the voltage of this DC bus to the DC to an AC voltage for the grid. So what is the main thing is this DC to DC converter is what we're going to talk about in this tutorial. The DC to AC converter will come in another tutorial, and that is what this challenge of this tutorial is. How do we convert a 30 volt PV panel to a high voltage DC bus? So let's talk about this DC bus. If you have a grid of around 200 volt AC, we would need a DC bus of around 300 to 350 volts. It could be even higher. If you're connecting to a three-phase grid of 400 volts, you may need a 600 volt or 650 volt DC bus. So therefore, the challenge is, how do we convert a 30 volt PV panel voltage to a high voltage DC bus? So let's go to the next slide. So I'm going to narrow down this problem. To do this conversion, how do we start? Begin with, we need to step up the voltage. That's the first challenge. So to step up the voltage, what are the solutions we can use? Number one, simplest, can we use a boost converter? Or can we use a transformer? So let's look into this. Let's go to the next slide. So let's look at the basic boost converter that we are all very familiar with. It's a simple structure: inductor, switch, diode, capacitor. Now this switch is usually either a MOSFET or an IGBT, could be any of them, and this DC source which is shown here will be a PV panel. Now to mention here, in this tutorial from now onwards, I will be considering the PV panel as a DC voltage, because I will not be considering the PV characteristics. That will come in the next tutorial. This tutorial is only to describe the operation of the DC to DC converter. So now, first things, this DC boost converter is quite often used, but let's look at this particular case. As I said before, we have a panel voltage of around 30 volts, and let's say we have an AC grid voltage of around 110 to 120 volts. So this means we need a DC bus of around 250 to 300 volts. So this conversion ratio will have to be 10, because we have 30 volts on this side, we need 300 volts on this side. That's a ratio of 10. And at the least, even if we are looking at a low voltage AC bus, let's say we just want 110 volts, let's not look at the step up factor. Even in that case, just take 30 volts and 110 volts. That's a ratio of 3.66. Now, what this means is, this is the best case of boost ratio. As the PV panel voltage drops, this boost ratio is going to go even higher, which means from 3.66 it will go to 4, and realistically it may go to 15. Now the problem is, when you have such a high boost ratio, this DC to DC boost converter is not recommended. The reason, when you have such a high boost ratio, the stress on the devices is very high, and therefore that decreases the life of the devices and also causes it to fail. So this is not a preferred option, even though it may be an obvious option. So now let's go to the next slide to look at what other options are there. So now let's look at our old option of a transformer. We usually use transformers to a great degree in a power system, but usually we use a transformer for an AC system. Like in this case, we are looking at two DC sources. We are looking at a PV panel of around 30 volts wanting to be boosted up to 300 volts, again DC. How are we going to use a transformer to boost up DC voltage? If you apply a DC voltage to a transformer, you will immediately saturate. The reason? Because the flux of the transformer is the integral of the voltage. If you apply a DC voltage, the flux will saturate, it will burn the transformer. And that's the problem. We cannot directly connect this. So there has to be something else in between these two, between the PV panel and this transformer primary. And this, whatever device comes here, has to convert this voltage to some form of AC. And I'll tell you what that some form of AC means. When we look at AC voltage, what we know is a sinusoidal voltage of 50 to 60 hertz. That's what I said, a smooth sinusoid of 50 to 60 hertz. That's our AC voltage, which appears at the power point in our houses and our offices. Now, that's not all that's there in AC. As far as a transformer is concerned, what is AC? AC voltage for a transformer merely means it has to be a periodic waveform where the integral of the voltage over a time period is equal to 0. And I'll describe this more in the next slide. So these are some samples of AC voltage. They don't look like AC. You would expect a sinusoid, but these are not sinusoid. The one above is a triangle. This one is a pulse, is a square wave. But these are still AC for a transformer. And why? The reason is this. This triangular waveform is a periodic waveform. It has a time period. This time period is equal to this time interval between this zero crossing and this zero crossing. Let's assume it is periodic. So this time period remains the same always. Also, let us assume that this positive peak is equal to the negative peak. What this means is, if we integrate this waveform over a time period, you will get 0 because the positive part is equal to the negative part. And the same here. Let's assume the time period is equal between this zero crossing and this zero crossing, and this time period is equal for a long period of time. So now, and also let's say this positive peak is equal to the negative peak, which means this positive part is equal to the negative part. The integral of the voltage over a time period is 0. Therefore, this will have 0 net DC component. If I apply this to a transformer, it will not saturate the transformer because a transformer will saturate for DC components or very low frequency. This is not a DC component. However, it's very important to know this has to be a periodic waveform and it has to be symmetric. Let's say I push this entire triangular waveform up. That means the positive peak is greater than the negative peak. If that happens, now the integral of this waveform is no longer 0 over a time period. Why? Because the positive part is greater than the negative part. There is a net positive DC component. And even this positive DC component, even if it is very small, with time it will saturate the transformer, because remember, the flux is an integral of the voltage. As time goes on, this flux will keep on building until the transformer saturates. So therefore, if this waveform can be applied to a transformer, that is very convenient, because guess what? This square wave can be obtained from an H bridge, and that's exactly what I'll show you in the next slide. So now this is the topology of an H bridge, which I mentioned before. Now here comes the PV panel, which is just a DC voltage source, and these are the devices that make up the H bridge. So the switches, which I show actually, which are not switches but are either MOSFETs or IGBTs, but in this I'll just call them switches, ideal switches. S1, S2, S3, S4. These are controllable and they can be switched on and off. The diodes mentioned here are the anti-parallel diodes across the switches. This is just to make sure that if there is an inductor at the output, the current does not break because of these switches turning off. So what this means is this H bridge is actually a very convenient design. You could build this H bridge out of individual devices. You could get MOSFETs with anti-parallel diodes, or you could actually get an H bridge pack. Many manufacturers actually supply this H bridge because it is so commonly used, and therefore we can use this to directly interface the PV panel. There is only one constraint here, and that is in the control. We must control it so as to ensure that the voltage produced at this terminal, which we are going to feed to the transformer, has to have a net 0 DC component, and I'm going to show you how that can be done. So let's look at the simplest way to control an H bridge. That is by using pulse width modulation. Pulse width modulation means we have a carrier waveform. This sawtooth waveform is the carrier waveform. The carrier waveform sets the frequency of the H bridge, or the switching frequency of the H bridge. So therefore, the switching frequency of the H bridge will be the frequency of this carrier waveform. So this is the time period between this zero crossing and this zero crossing. The frequency corresponding to that time period will be the switching frequency of the H bridge converter. Now, the signal shown here is a modulation index. The carrier waveform has a peak of unity. the modulation index can be a maximum up to the peak of unity. So now we are going to talk about one case. Let's say this modulation index is at 0.5, and I'll tell you what that 0.5 means. When you compare a sawtooth waveform of unity peak with a modulation signal of magnitude 0.5, you end up with this waveform. What that means is this. Let's say we are controlling the switches. I'll just go back here. Let's say we want to control this switches so as to produce a voltage here. This voltage has to be a square waveform. What that means is, let's suppose I turn on the switch S1 and S4, that is the diagonal switches. In that case, the upper terminal here will have a positive voltage, negative terminal here will have a negative voltage. Let's suppose I switch off S1 and S4 and instead turn on S3 and S2. Now the reverse happens. The upper terminal on this output becomes negative, the lower terminal becomes positive. So we now have the lower part of the square waveform. In this way, that's exactly what we do here. We perform this calculation. What we say is this: when the modulation signal is greater than the carrier waveform, turn on switches S1, S4. That's what happens. When it is less than the carrier waveform, you turn off switches S1, S4. So you see, that's exactly what happens. I marked this crossover point. So it is on when modulation signal is greater than carrier, it is off at the other time. And S2, S3 is exactly complementary. So the reverse of it, and that's exactly what I've shown you. And if you see, if you use this method on this converter, that is exactly what I said, turn on S1, S4 together, you'll have a positive voltage. Turn on S2, S3 together, you'll have a negative voltage. What that means is, you'll have the positive pulse of the square waveform here, the negative pulse here, and these two also. In this way, we can generate a square waveform with this switching topology. The only constraint, as I said, it has to be a 50% duty ratio. And this one is important because the pulse width of the positive part is equal to the pulse width of the negative part. That's the idea of the switching frequency of 0.5. And I'll tell you what happens if you don't have a switching frequency of 0.5. If you don't have a modulation signal of 0.5. This is a case of what happens if the modulation signal is lower than 0.5. You see what happens? I've moved it a little lower than 0.5. Now, I'm going to apply exactly the same logic, and you see here, in this case, since it is lower than 0.5, the modulation signal, S1, S4 now has a pulse width which is lesser than the pulse width of S2, S3. What this means is, the positive part of the square waveform, or rather the rectangular waveform in this case, will be lesser than the negative part of the rectangular waveform. We don't have a square waveform anymore, we have a rectangular waveform. And the result is there will be a net negative DC component. And this net negative DC component, if you apply it to a transformer, you will saturate the transformer. So this is the reason why 50% duty ratio is extremely important. So the modulation signal has to be 0.5. That's a constraint. Now, this puts another problem. Okay, we now have the capacity to generate a square waveform that we can apply to a transformer. So we can boost up this voltage. But the problem is this: when we use a power electronic converter, we want a variable output. We have an AC output, but this AC output is not variable. It only depends upon the PV voltage. But we want to be able to vary the AC output voltage even if the PV voltage is constant. How do we do that? The problem is this: usually the control is always through the duty ratio or the modulation signal. But the problem is this, as I said before, we cannot move out of 50% duty ratio. The modulation signal has to be 0.5. So therefore, how do we control it? Because that's the only handle we always have. We cannot change the frequency of the AC output. We can change the frequency using the carrier waveform. If we change the frequency of the carrier waveform, we change the frequency of the AC output voltage. But that will not change the RMS voltage of the output voltage magnitude. Because the RMS voltage of the AC voltage is merely the integral of the square of the voltage over a time period. That's not going to change. That only depends upon the magnitude and the pulse width. So we are now in a bit of a problem. What this means is, how do we change the output AC voltage? And there is a solution. we have to bring in a third state. Now we have a positive part, we have a negative part, but we have to bring in a third state, and this third state is a 0 voltage state. And that's what I'll talk about in the next slide. So in this slide, I'm going to talk about how do we switch that edge bridge so as to be able to produce this 0 voltage state. And I'll just show you, even before actually describing, this is what that 0 voltage state is going to look like. You see, this is the output voltage, output AC voltage. It has a positive part, it has a negative part. The width of the positive part is equal to the width of the negative part. The peak of the positive part is equal to the peak of the negative part. But there is now a 0 voltage state. And this is how we are now able to change this AC output voltage. And I'll tell you how. I'm going to show you all the switching signals of all the 4 switches. Alright. Now, before I go into, I'll just go back to the figure and I'll tell you about a constraint. The first constraint when you switch this converter is switches S1 and S2 are complementary. What this means is, if S1 is on, S2 has to be off. If S2 is on, S1 has to be off. They cannot be on at the same time. The reason, if they are both switched on at the same time, you will short circuit this voltage. Here, the voltage is a PV panel. A PV panel, as I've told you in the previous tutorial, can be short circuited. It won't be damaged. But even then, you do not want to short circuit any voltage source. That's the reason why, and I'll tell you later, that even though we have a PV interfacing a PV panel, we will be using an intermediate DC capacitor. In the next tutorial, I'll show you how that happens. And when we have an intermediate DC capacitor, we cannot short circuit that. The reason, a capacitor has no current protection. If we short circuit a DC capacitor, we will damage the switches and we will damage the capacitor. So that's number one. Similarly, switches S3 and S4 are complementary, which means when S3 is on, S4 has to be off. When S4 is on, S3 has to be off. So this is a major constraint in this converter. Other switching control strategies are okay. So with this, let's move on. So coming here, let's say switch S1. As I said before, we are still going to continue with our 50% duty ratio. So switch S1 is switched at 50% duty ratio. So you can see on time is equal to the off time. Switch S2 also has 50% duty ratio. So the on time is equal to the off time. And as I said before, S1 and S2 are complementary. So when S1 is on, S2 is off. When S2 is on, S1 is off. They cannot be on at the same time. Realistically, there will be actually a dead time. So before, when S1 is turning off, S2 will not turn on at the same time. It will turn on a little later. But that's an implementation strategy. I don't have to talk about it here. Now, similar case here. S3 and S4, also 50% duty ratio. S3 is complementary to S4. You see, they are never on at the same time. With this now, before I was saying, we were turning on switch S1 and S4 together. So, S1 and S4 were on at the same time. What that meant was, when S1 and S4 are on at the same time, you have a positive voltage. Let's look at this part now. Between these two lines, S1 is positive. At the same time, between these two lines, S4 is positive. The result is a positive voltage. Now, supposing for example, S4 is not on during the entire period when S1 is on. So during this part, S4 is off. S1 is on, but S4 is off. So therefore, one switch will not do. The result is the output voltage is 0. And the same in the negative part. Before, S2 and S3 were on at the same time, and when they are on, they produce a negative voltage. For example, in this period, S2 is on, S3 is also on. The result is a negative voltage. And here, S2 is on, but S3 is off. One switch will not do. The result, you have a net AC output voltage of 0. This is how we produce the voltage 0. We are now phase shifting these voltages, these firing signals, with respect to the firing signals of the first leg. So we can now divide it into two legs. S1, S2 form one leg, S3, S4 form the second leg. The firing signals of the second leg are phase shifted with respect to the first leg. And if you notice, when they are phase shifted, let's suppose for example, this is our phase shift, because if you look, let's look at these two, S2 and S3. these two are almost symmetrical, but there's a phase shift now between these two. What this means is during this phase shift, the voltage is 0. So if we can control this phase shift, we can control the width of the 0 period. And with this, we now have a control strategy. And this is what it is. You can just read this part. So now the question is, we now have a control strategy, but how are we going to achieve it? And for that, there is a way to achieve it. The reason is this, the solution is simple. The solution is we are now going to use 2 carrier waveforms instead of 1. Okay. So let's suppose we had initially one triangular waveform, rather one sawtooth waveform. Now we have a sawtooth waveform for the first leg. We have a sawtooth waveform for the second leg. Modulation signal is 0.5 still in both cases. But the phase shift between these 2 carrier waveforms will become the phase shift between the firing signals of these switches. And that phase shift between these triangular waveforms, or rather sawtooth waveforms, is what will produce the 0 voltage vector. And that's how we can control it. We can control it by producing a phase shift between these carriers. Now this can be done usually in an implementation, can be done in digital signal processors, because in digital signal processors you have to upload a certain value into the register corresponding to the sawtooth waveform. You can always upload a different value, and therefore you can change the phase shift with control at every 0 crossing. So I'll just talk about some extreme cases. First is, let's suppose the 2 carrier waveforms are in phase. Exactly. See, here they are. I've shown this line for that reason. They are exactly in phase. When this happens, the AC voltage is 0. Why? Because there is absolutely both the signals are in phase with each other. You understand? So therefore, when S1 is on, S4 is always off. And if S4 is always off and S1 is on, there will be no positive DC voltage at the output. Similarly, the vice versa. When S2 is on, S3 is always off. The result is the output AC voltage will be 0. I would recommend that you try it out yourself and check this waveform. The other extreme, let's say they are phase shifted by 180 degrees. Here this is exactly what I say. When this modulation, when this carrier waveform is 0.5, the other carrier waveform is at its peak and is starting again from 0. This is the case of 180 degree phase shift, and this is when we get the maximum AC voltage. I would again suggest that you try these waveforms out by looking into how this switching happens in a circuit. So therefore, this is the conclusion. Usually we always use duty cycle control in any conventional DC converter. That's how it is. We have a carrier waveform, we have a duty cycle. The duty cycle changes. We change the duty cycle by changing the modulation signal. But the problem is here. In this case, we want an AC voltage. Therefore, we cannot change the modulation signal. We always have to keep it 50%. This is the reason why we have now come up with the concept of phase shift control. So we are not changing the modulation signal. We are now coming up with 2 carrier waveforms and changing the phase shift between them. And this is how we are going to control the AC output voltage. And as I will show you in the next few slides, this is how we can change the output AC voltage that is available from this PV panel. So this is the total circuit. There is the PV panel. Actually, as I will tell you before later, this is not exactly the PV panel, but for now this is good enough. This is the H bridge, which I already discussed before, and finally the transformer. So now I won't go beyond this because that will be reserved for another tutorial. But what I'm going to talk about now is how, for a PV panel with a certain constant voltage, we can now change the switching of this H bridge to get a variable AC voltage, a high voltage, variable high AC voltage at the secondary of the transformer. Now a word here about the transformer. This transformer will be a high frequency transformer. This is not like our typical distribution transformers of 50 or 60 Hertz. The reason, the frequency output of AC voltage at this point is a high frequency square waveform. It is not a 50 Hertz sinusoidal waveform. It's a high frequency. Typically these switches these H bridge can be switched at anything from 10 kilohertz to 100 kilohertz, depends upon the switches. If it's simple silicon switches, you might want to use just 10 to 20 kilohertz. If it's silicon carbide switches, you might want to go between 50 to 100 kilohertz. And that means this transformer will have to have that switching frequency. The advantage is we use a ferrite core transformer rather, and therefore the size of this transformer is much smaller. Therefore, the advantage is the DC to DC converter is compact. Beyond this high voltage AC that is produced will be rectified by a diode rectifier, and then there will be an inverter. I'll talk about this in another tutorial. But for now, I'll show you some simulation results. So now, as I said before, we can change the AC voltage by changing the pulse width. I'll show you some sample simulations. Here the PV voltage has been assumed to be 35 volts. The transformation ratio is that the primary of the transformer has a rating of 35 volts and the secondary has a voltage of 120 volts. Now, as I said before, this is just sample voltages. Later on, I'll design an actual tutorial with power extraction. Now, here I have chosen the phase shift to be 30 degrees. So what that means is that this voltage here is so slim. Just notice how thin the phase shift is. And this is what it means when you have a phase shifted voltage of low degree. The lower the phase shift is, the smaller is the output AC voltage. Now let's go to the next one. Here I'm showing you a phase shift of 90 degrees. You see the pulse width is now bigger, much bigger. And the zero voltage part is now much smaller. So therefore, this means more AC voltage, and if I rectify this, it means more DC voltage. Finally, the next slide. And this is the last extreme case. This is when the phase shift is 180 degrees. And as you can see, this is now a square waveform. It has no zero part. You see, there is no part where the AC voltage is zero. This is a pure square waveform. And therefore, with this, I'll show you what this shows is that this produces a variable AC voltage with no DC component by switching the H bridge, and this allows us to use a transformer, a high frequency transformer though, but a transformer still, to boost up the voltage of a PV panel from 35 volts to anywhere between 120 to 400 volt AC. And this is how it's done. So this is the conclusion of the PV of this tutorial, and at this point I will just show you these other links. Now there are some other links on this left hand side. The first link is home. I'll just open it in a new tab and this will take you to the home page. Now the next one, which is a tutorial, if you click on it, it takes you back to the tutorial from which we came from. That is the tutorial on this topic, power extraction from a PV panel. And the last is, that is what's called package. This takes you to the external site, which is my Gumroad site. Gumroad is an e-commerce website where I host the simulation files for each tutorial. And here is where you'll find the simulation files for this tutorial, which is switching strategy of a PV panel. So if you're interested, you can check it out. And with this, I'm almost done. Feel free to look at these links or else look into the site. And if you still have any doubts, feel free to email me. Thank you so much for watching.